And so we're very glad that we can go to his talk now about AI for energy systems in every country. I guess a big topic, also here in the Netherlands, as we're pretty dense population, and he's gonna drop a vision for developing tools for the energy transition, which is obviously a very big transition that we have to make with us all, with AI methods such as multi-agent reinforcement learning and also deep learning. The co-director of the TU Delft Energy Lab, but also research associated at the Imperial College in London. We're very glad to welcome him to the stage for our next keynote talk. Jochen Cremer.
Yeah, thank you very much. All right, after this physical exercise, I'm trying to bring you now a little bit closer the exercises we are doing with the energy system. So it's a pleasure, first of all, to be here and to deliver this keynote to you. Thanks a lot for the invitation. And I started with showing you a little bit like the big trends which are happening currently in the energy system. So I'm kicking off with that. So the first trend which we are experiencing is that we have significantly more smart devices in the upcoming decade in our systems. So if you think about households, this is all connected to electricity systems. So we expect a large increase penetrating through security and surveillance, lighting, entertainment, energy management, which all have new smartness inside their controllers. Right? So we have a lot of new devices which are being implemented, and they try to interact with each other. The second trend which we have is we are increasing the number of electric vehicles as we have to move away from fossil fuel-based transportation. So this is the second big trend which we have, where also in the next decade we see almost an order of magnitude in terms of market in the US only, which is being changed or increased in terms of the number of electric vehicles and also plug-in hybrid electric vehicles. So these are the two big trends which are happening, which makes the energy system much more complex. So we are increasing the number of these smart controllers, of this, which start to interact with each other, which are coordinating. But all of this is connected to the big grid, which is really interconnecting countries, if you think about it, right? So it's really this this high voltage grid. And the physical laws of this high voltage grid, when it was designed, are still present, Kirchhoff's law, right? So, so this means that an existing system, the electricity grid, is being changed with a new set of devices, controllers, smartness, etc. So that's a challenge, because that isn't a grid which was built decades ago, and we need to find new ways of controlling the system, as I will point out. However, what we currently do is we are concerned in the energy world with a different topic, which is to get independence on Russian gas here in the European Union, which means that basically we are trying to replace the huge influx of Russian gas into the European Union, and still that means we are still having fossil-fueled energy. So what we actually should do, and we're concerned about, is to replace this large generation units of coal, nuclear power with renewable energy, photovoltaic and wind and so on and so forth. So that's what we should do, and at the moment we are doing something different. But if we're managing to replace those, we have some issues in the system, as mentioned. So this complexity is increasing, but then also you may be familiar with the grid frequency, so that's a kind of synchronization metric which we have, 50 hertz. So if a disruption in the system happens, the system frequency may deviate slightly. And the issue becomes now that this slope here, through this smart controllers, as they all try to regulate themselves, is becoming steeper, which means that the previous control methods, which means primary and secondary frequency control, which are being implemented in large system control rooms, these are not functioning anymore as they were designed for. And this is something which we need to address. So at the moment, all of these controllers here are way too slow to address the steepness of the slope. And as you can imagine, if the frequency goes under a certain threshold, the system may collapse, and we are facing a total power blackout in a country. And that is really, really severe if this happens. So my research is about avoiding those issues and finding new methods how we can control the devices which we have in the electricity system. So, and there are two paradigms which we have in electricity system, which are more or less accepted, which we are working towards to. So the first one is to move from hierarchical control towards decentralized control, right? And this means that in the past you had this huge generation units in the transmission system, which were then where the electricity was then transported to the demand centers, let's say cities, and then distributed within the cities to the neighborhoods, to you in your households, that you can consume the electricity. So, and now if we manage to control those units locally, right, then, and they become autark, then they can be basically disconnected, right, and this improves the resiliency, so power blackouts would not occur because you have already managed all this energy balance in the local unit. So that's the first way to basically trying to have this sector coupling, right, inside local neighborhoods, so that they are not really a concern anymore for the big electricity grid. And then the second trend is about still having faster methods which can analyze the data of these devices which they provide in the future. And this means to centralize the data processing in control rooms, right? So system control rooms, let's say here in the Netherlands, TenneT, which is the system electricity system operator. So they have two things to manage. So the first one is the power domain. So this is where the electricity flows from which area to which area within the Netherlands or European Union, as this is all interconnected. But then the second challenge is to make this communication work on a national level, right, or even internationally. So there you have control units, control centers, you have switches you can trigger in substations and so on. So you need to optimize these. And lots of more information is available. The system is being operated completely different. So basically, this is the second paradigm, is to properly design intelligent control based on data processing techniques. Okay. So why I think artificial intelligence is playing a major role in the future in these two paradigms is because of two challenges which we have and two approaches which AI techniques can contribute to. So the first challenge is, as outlined, smart homes, right? Or more electric vehicles. So we have highly complex systems in the future. But through artificial intelligence, we have also a new set of techniques which we have. For example, multi-agent reinforcement learning, which is really decentralized and learn in real time to improve the local system. So the second challenge which we have is that a lot of standard software is very slow, which means let's assume you're modeling the electricity grid in every single detail. So considering dynamical simulations and so on. So this means that simulating grid conditions is extremely slow. We can't do this in real time. However, once you have trained a machine learning model, it is super fast because it's just a feed-forward function, right? So the question just becomes then, how do you train this model? All right, so these are two challenges, two let's say, kind of set of tools or techniques which AI can provide to, which are really nicely fitting to each other. And I'm going to talk to you now a bit about the research which we do in these two areas, right? So the first one is about the decentralized control. So there I'm presenting to you how an aggregator is aggregating these different devices and then offering them to the energy market, right? So for example, this real-time response, so we have this frequency drop which I showed, and then an aggregated set of electric vehicles could immediately respond with their energy consumption, with their energy demand. So, for example, charge a battery in real time, and this aggregator is offering this type of flexibility of this demand to the market. However, there are some challenges of these aggregators, which are related to that they basically have to coordinate many clients, so in the order of thousands or even millions of different devices or customers, and the customers would like to preserve their privacy, and it has to be real-time fast, this type of algorithm. So that's not an easy challenge. So basically, you don't know much about your customers. you can't use any information from them. And it has to be super fast, the decisions you make, and you want to provide the flexibilities of systems. All right. So what we developed is an approach based on multi-agent reinforcement learning, which I'm now going to introduce. But just to summarize that the centralized approach would fail. So let's assume you have full knowledge. The centralized approach basically requires full knowledge of the customers, which is not available. So we modeled then an aggregator agent. So that's basically this aggregator who's trying to incentivize by basically paying their customers, which are connected to this aggregator, a small amount of money to change their power rates. So this is their consumption, which they would like to consume in this moment in time, right? So that's, for example, household appliances and so on, dishwashers, and so on. All right. So then we model this aggregator agent and a household agent. So the method we use is then reinforcement learning. So basically, we have this agent receiving a reward. So if we are talking about the household agent, then we are talking about the incentive being received, but then also the dissatisfaction of not fulfilling the energy they would like to consume at that moment. And the agent would then perform this action, which is to reduce, for example, the power demand. The environment here is the energy system, as I will show you later. And then multi-agent reinforcement learning is just the way of doing this multiple times with different agents and interacting with the environment, right? So the environment, maybe to summarize that, is basically the kind of electricity grid. So we have the utility. So this is the one which is placing some global constraint of the aggregated units. So, for example, the total power consumption of this neighborhood has to be below a certain threshold, right? So this is the capacity C. Then we have the aggregator agent. So that's this agent which is placing the incentive through the actions to the individual customers. And then we have the customer agent, which is indeed aware of the local household. So this means to know when, how the characteristics of the dishwasher is, and the electric vehicles, and so on. So it has more information, where then an internal scheduler would schedule these devices, like as similar to energy management systems. So yeah, we have different type of agents: aggregator agent, customer agents, and we have this environment. So the aggregator agent, maybe just to briefly say, so it tries to the objective is to minimize the energy consumption above this target, about the threshold which I mentioned, and minimize the paid incentives to the cumulative incentives to all of the customers. So it observes the total energy. You have this target reduction, and then the action is to place this incentive rate, and we have this reward. So the participant agent on the other side is maximizing the earned incentive and minimize the dissatisfaction, right? It observes the state of the household appliances, so if the dishwasher is running, if the EV is at the moment charging, and so on and so forth. And then the action is basically to reduce the aggregated power rate of all of these devices in the household. So there are three different types of devices which we have, or appliances. So one is the time shifter one. So this is the devices which you can basically shift the power consumption to a different time. So from high peak periods possibly to low peak areas. So let's say you plug in your EV in the evening, but actually that's not necessary to charge it right away. This could be shifted to start in the middle of the night, so that it's still being charged in the morning. Then the second type of devices is power curtailable appliances. So this means that you can curtail the power of these devices. So an example would be lighting or the air. So lighting means you dim basically the lighting, or air conditioner, and so on. And then the third type of devices is non-shiftable appliances. So these can't be reduced in power. All right, let me show you a brief case study. So we developed this algorithm on deep reinforcement learning using the Pecan Street database. So this consists of 25 households. We trained it then over 5,000 episodes. And then we consider different type of devices. So dryer, washing machine, dishwasher, electric vehicles for the time-shiftable devices, and then air conditioner for the power curtailable devices. So let me walk you through the results. So the first one is we have here this threshold, right? So we deploy either no demand response. So this means that there is no smartness happening. Every consumer is just consuming electricity as they wish. And you can see that we are above a certain threshold with this aggregated 25 households. This is the yellow or orange curve. Then we have our proposed approach based on MAL IDR. So there you can see that we are reducing it most of the times, but there is some peaks which we have not reduced, so the agent was not able to learn that, or the incentive was not high enough. So here you can see the peaks of the incentives. And you can see that basically these align with each other, right? So we have some reduction from orange to red here, and these are the times when the incentive has been paid. So then we compared this with a myopic baseline. So this is basically an approach which has more information available of the households, and can basically schedule and bring this up to below. But however, this myopic baseline has full knowledge about the system, so that's not available. It's just to illustrate how good the algorithm, how good it would be possible to perform here. And you can see that the myopic baseline also has a lower incentive, which has been paid. But so that's basically the results. In an individual household level, you can see, so we just zoom into one of these 25 households. You can see that we have the no demand response, so this would be the baseline, where you have here this peak around 5 to 7 p.m., so this is one day, and this is the incentives as shown beforehand. So the reduction just illustrates the reduction on a single household level. But what is quite interesting is now to look into the different devices which has been scheduled for this household. So you can see that there has been some curtailment in the AC, so this is the air conditioner, which were reduced at the peak, right? And we see some shift. So in light color, you always see the previous one. So this would be the desired energy demand. And in bold, or in this thicker color, you see the adjusted one by the proposed algorithm. So we experience some shift in the washing machine and in the electric vehicles from this area to this area, and then this kind of curtailment, which I illustrate. So that's the result. Let me now move to the second direction, which I emphasized earlier. So I mentioned we have these two paradigm shifts which you need to occur. One is this decentralized thinking, right? So more local coordination and control. So the second one is to process in real time, in the control room, the data and extracting information so that we can run the power system more reliable, right? So avoiding power blackouts. And just to start off with this motivation, we have here just to say, in Texas last year in February, there was one of the power blackouts which happened. They happen from time to time. And it was very interesting to see that the impact you see here, Houston, basically two figures, right, which were just a few days different. And you can see there is just a little bit of less light. It was a partial power blackout. But still, the result was a 200 billion US dollar damage. And most scary is basically that we were seconds away from a total power blackout in the entire state Texas, right? So this is, here I'm showing just Houston. So if the system operator would have reacted a few seconds later, this is what the reports showed. We would have, or the people in Texas would have realized there was a total power blackout, which, so if this happens, it can take up to several months until the power system is being restored. So we need to avoid this at all costs. These power blackouts to predict is very hard and difficult to do so because we have this complex energy system. But we have worked in the last decade on techniques from machine learning to predict these power blackouts. So the standard method would be to use numerical integration of the dynamics. So you could model the electricity system in detail, considering the individual controllers, putting them into Modelica, right, and then running typical blackout scenarios. So let's say a wind park is an outage, or a generator is an outage, or a tree falls on a transmission line, or whatever. So different type of contingency scenarios. And you are then simulating all these contingencies, and you will figure out that it is just taking for the Dutch system, for the electricity grid, if you model it in full detail, up to 30 to 40 seconds for a single simulation on a standard computer. And this is unfortunately too late to prevent power blackouts. We need to have this information in real time. So in contingency occurs, we need to know exactly now in real time if the power blackout is imminent or not. So because then the system operators can obviously act. So to say the binary classification is a separate approach where you're just interested in predicting binary if a power blackout occurs or not. So you train offline a machine learning model. You're creating these scenarios because there you have the simulation time. And we did this type of research, and we figured out that, yes, it's possible to predict that. but we will face very large inaccuracies, and this has to do with constant system changes. We can't simulate all different conditions, and so on and so forth. However, the objective still keeps the same. We still believe in this, as it is so important to do. And our goal is basically to achieve accuracies of over 95%, because then, according to our conversation with system operators and from project outputs, they would rely and use this technique in operation. So what I'm giving you now is a bit the insights from our research which we did. So first of all, what is important to realize is that we have this security boundary, right? So this is basically the binary boundary between unstable system condition and stable condition. So you have here two variables which describe the state of the system. And yeah, sometimes you see that the predicted and the actual security limits, so this is the security boundary here, are not exactly the same. So you have inaccuracies, and that can be quite severe. We have this class imbalance problems, the cost sensitivity issue, which means that we have false positive and false negative in binary classification as the two types of misclassification. And one is more severe than the other. So let's assume you're thinking that the system state is secure, but it's actually insecure. So then we would miss a power blackout, and that is extremely bad, right? So I showed you this number earlier for what it could lead to, this 200 billion, extremely large figure. So there is a huge imbalance in terms of the costs and the misclassification may occur. There is also a second issue which has to do with the class imbalance. So we have significantly more negative than positive cases, which means here more secure cases than insecure. As you can imagine from historical observations, there's very, very limited information available of power blackouts, right? So this means that we need to enrich databases with synthetic generated data. Otherwise, the machine learning method would fail because we have just too little data. All right. However, interestingly, a classifier cannot only classify points. So to evaluate basically if a point is positive or negative, but we can also rank points, right? So the points here mean the input to the classifier. And we get other information. How positive is this point? How can we can compute scores and so on. Which is useful information, and it tells us something about the confidence of the classifier, right? But we can't directly use them as probability estimate, which system operators would like to have. So they would like to see the information of how likely it is that the power blackout is occurring, right? So probabilistic information. But we can't necessarily do that. So we need to first transform these output scores. Let's say here a standard decision tree where the score is then computed of, let's say you have one data point and it falls into one leaf node, and then the score is being computed based on the training data and how much training data, or the share of positive points in one leaf node based on the training set will give you this score. So you have a testing point, it falls into one leaf node, and the score is then one fix, for example, which is here on the left side. So we can't use that. But what we can use is to perform plot scaling if you use random forest or such techniques to just fit a sigmoid function on top of it, and then we can use probability estimates, which are more accurate than just using scores. So then if we have that, we can actually quantify this risk. So we can quantify how likely it is that the predicted outcome is secure or insecure. And we can also use these costs for false negative and false positive, where, as mentioned, one is much bigger than the other. And then we have also the probability that a contingency occurs. So you may know high windstorm in the system, so it's very likely that there is a tree falling on the transmission line, right? So we can compute these probabilities based on weather data. So we have this PC, which is the probability for contingency. We have the probability output of the classifier, and we have the cost. We see two costs, so we can basically now think about we would predict with the lowest residual risk, and that's basically now a more conservative use of the classifier, and actually this information here could be updated in real time, which is interesting. So you train a classifier offline, afterwards in real time you can update it based on actual information from weather measurements, which is great. All right, so we tried this then on the French transmission system, working with the French transmission system operator, RTE. So in a large European project, there we figured out, okay, you could actually also simulate a few conditions in real time. So you have a little bit of computational time, So if we do that here, so this is the number of simulations on x-axis. So if you do that, so if we would not simulate any point, you would just use the classifier predicting possible contingencies. You have this risk metric, right? And this is the total risk of all of the points, so the summation of all of the kind of possible scenarios which could happen. And so if you now use a type of ranking of this risk and to analyze with the simulations, so with this as computing the real labels, if you do that now for the top highest risk, you can reduce the risk with a few simulations only. So only here means, by the way, 20,000 simulations. We are talking about a large French transmission system, right? Yeah, so basically here you can see that the risk with our approach is decreasing quite drastically, which is interesting. So maybe you can reduce the risk of relying on this classifier by just running, I don't know, a few hundreds of simulations, and that's already quite good. All right, so now, before I'm showing you this, I'm almost at the end. I'm showing you some new research which we have done, which is a completely different idea. So now we are thinking, okay, it's not possible to anyway simulate all of these possible contingencies. Could we actually do something online? So just learn a machine learning model online in real time, so after the fault occurred, right, or the contingency occurred, and we would like to get the same information about security or insecurity or the system stability, right? So here what we are showing is a new type of machine learning model where you see now 3 measurements in the system. So this is phase angles, which describe one system state variable. And you have a very small system. It's a test environment. You have 3 measurements, and they are being recorded. Nothing happens. But soon something will happen. And you will see. So basically, in this moment, there has been some disruption in the system. And you can see that the phase angles are diverging in various ways. But at the same time, as soon as the disruption has happened, this disturbance has happened, a machine learning model has been trained in real time. So the training has started in that moment in time. And you have this predicted, the prediction here as this dashed curve. And we can see that now, even though the training has just had a little bit of information of the first, the first moment after the fault, so right, it uses post-fault data to train, still the method is able to predict where the final trajectory will be. So that's a new type of thinking, which we are at the moment developing in the lab. But we have not concluded this research. So it's a little bit showing you pre-results. Anyways, let me conclude. So what is interesting from this type of research within energy systems, so as mentioned, this was a bit a detour into energy systems, what's relevant there, the problems we have in terms of complex energy systems and so on. But AI has the chance, or the huge set of AI techniques has a chance to support these decentralized and centralized processes. So that's what my research is about. To discover those methodologies and adjust them to electricity systems. We have also I have shown that BAL preserves the privacy and computational efficiency. It's only 2 milliseconds. But what we need is this kind of real-time techniques, which can really fast train machine learning methods on very limited amount of data. So that's, for example, for us also future outlook and future development of our research activities. And with that, thank you very much.